Water's not the only material with which we could fill a sphere. If we filled our sphere with, say, motor oil, alcohol, honey, we might get a different index of refraction. We would get a different index of refraction. No two materials, as far as I know, have exactly the same index of refraction. However, for most liquids, the index of refraction doesn't vary a whole lot. I haven't investigated that many common liquids, but the one with the highest index of refraction we can easily get our hands on seems to be honey. Honey seems to have an index of refraction around 1.5, whereas water is around 1.33, and that really makes for some significant differences in lenses that are filled with honey as opposed to lenses filled with water. Most glasses and acrylics have fairly similar indices of refraction. Some glasses go up around 1.4, and I guess some go somewhat higher than that, but they get kind of expensive. In any case, let's say that one way or another we fill this sphere with some other liquid like honey that has a different index of refraction, and we're going to do a generalization and call the index of refraction n. Well, the whole analysis proceeds just as it did before, except instead of 1.33 we're going to use n. And the angle of refraction theta r is going to be delta x over nr instead of delta x over 1.33r. That'll follow directly from Snell's law, and it won't really be a problem. Okay, the focal length of the lens will then be, or the spherical object, will then be the adjacent side of this triangle where we have this angle instead of the angle that we saw in the preceding figure. Now this is actually a little bit neater than having to carry that 1.33 around. It's a lot easier just to write down an n. The algebra is exactly the same as what we did before. Every step is pretty much the same. I've been a little more explicit here. I've put the denominator here over common denominator. And for some reason I used nr squared here, which is not necessary. I could have used nr for the common denominator. But it doesn't hurt to use nr squared. It's just not quite as neat. Multiplying by the reciprocal and then dividing through by the r, we see that the focal distance is n over n minus 1, and it seems like I've made up for having an extra r here. If I divide r into r squared, I do get r, so I'm going to have an r down here. Okay, so it's going to be n over n minus 1 times r. Now before we saw that we got 4r when n was 1.33. Well, 1.33 over 1.33 minus 1 is 1.33 over 0.33, which is very close to 4. If n is 1.5, as if for honey, what's n over n minus 1? Well, it's 1.5 over 1.5 minus 1, and that's going to be 1.5 over 0.5, or 3. So for honey, if it does have an index of refraction of 1.5, and I haven't measured that precisely, so I won't swear to that, but I think it's fairly close, then we're going to have focus at 3r instead of 4r. That's a significant difference in the point of focus for what appears to be just a small difference from 1.33 to 1.5 in the index of refraction. If we go all the way to n equals 2, well, if n is 2, then 2 over 2 minus 1 is 2 over 1, which is 2, and we're going to converge at 2r. Now where's 2r? Well, that's right at the other side of the sphere. Here's the sphere. Here's where we come in. If the focal distance from here is 2r, that's just a diameter. That's going to be right over here at the other side, and everything's going to focus to a point on the other side of the sphere if we happen to have some liquid for which n equals 2. Now let's look again at how the images form and blur out and then magnify. Okay, kind of neat. So for n equals 2, that's really the transition point where the image, or the focus really does occur within the sphere, or right at the other edge of the sphere. If n is just a little bit more than 2, the focus will occur in the sphere. Now one reason diamonds have the spectacular reflecting and refracting properties they do is because the index of refraction of diamond is around 2.4 or something like that. You can look that up. If n was 2.5, for example, if we had 2.5 over 1 minus 2.5, that would be 2.5 over 1.5, which is 1.66. So we'd have focus at 1.66 R, well within the sphere itself. Not that we have many spherical diamonds. In the first place, diamonds are hard to cut in spherical shapes. In the second place, when they do, they don't have all the neat light reflecting properties that you get if you have different facets. But for two reasons, we don't have many spherical diamonds. One is it's real hard to cut a spherical diamond, and two, even if we did, they wouldn't look that great.